So I want to start with why is that not working? Hold on.
Oh gosh, what now?
I have to share, I guess.
Yes, okay, so they can't see it yet? You're sharing, there you go, should be. All right, can you see his screen?
Well, what's not writing? Why is it not writing?
Okay,
Hold on.
Lord. Okay,
Yeah, we see everything,
okay,
and
good.
But
please
you don't
try to write something.
Yes, he just
That's
did.
what's not
All
happening.
right, hold on. Let's try, this meeting is being recorded. I wonder if you try over here, that black pen on the,
Oh, that's it. I'm
Okay.
sorry. I
No,
didn't.
it's okay.
Okay, I got it now.
let's try it again.
Yeah.
Try to make it happen. Yeah, you don't want to turn
Alright.
that off. Okay.
So
let's try. Okay, yay.
It works.
Yes. So I want to start with just mentioning in 1892, in Burrell's thesis, he made the suggestion that you should be able to extend the property of unique continuation to some large classes of functions defined on compact sets without interior points. And the two, so here I'm going to consider just two of these sets. One is R of X is equal to the uniform closure of the rational functions with poles off X. And RP relative to dA will be equal to the LP closure of the rational functions. And one of the things that I don't know how much I'm going to say about this, but Burrell's thesis led directly to quasi-analyticity. And I'm going to use that later. And I'm going to use the Gonchar column on theorem. But before that, in order to get a set, compact set with no interior, there's a classic method of doing that, right? Namely, you build a Swiss cheese. That is a set, the unit circle, and I'll remove circles from the inside such that the sum of the lengths of them is finite. Now, this is, if you look at some of these things later that Fugler was doing on finally holomorphic functions, I don't know whether they constructed any examples, and it's hard for me to imagine you can do it without this sort of an arrangement. So let me, I want to talk this Bill Allen. Back in the late 60s, well, let me back it up just a hair. If one of the things you definitely you need, I want to have, I need to have R of X is not equal to C of X. Otherwise, we're not going to get any property of unique continuation. But oddly enough, back in the 60s, there was only the way that we knew that a Swiss cheese had positive area was through a theorem of 1931 theorem of Hartogs and Rosenthal, which said that if the area is 0, implies R of X equals C of X. Okay, and so for a Swiss cheese, you have an automatic annihilator, namely DZ. And so the conclusion is that R of X is not C of X, so it must have positive area. And at a lunchtime conversation, I mentioned to Allard this thing, that went on for about 30 years or more, with this indirect proof. And what Allard showed was, let's let me get what this, that if you take vertical lines, let me so let me put another one here, just for that. Almost all vertical lines, with respect to arc length along the boundary there, along the axis, meet the Swiss cheese in only finitely many times, so that the thing looks like you have a positive measure, because lots of these lines will have positive measure, almost all of them. So, but this gave a little something more than at the time. So if you have P and Q, 2 points, well, if you any 2 points, almost any 2 points, you can move around the Swiss cheese on the boundary and wind up at Q. So you can connect almost any pair of points by an arc. Now I'm going to make use of that as we go along. Okay, I don't need that. All right, so yeah, and one other thing that I am going to use, that if suppose I have if f is rational on omega n, let's call this, you have finitely many pieces here, then if you take the nth derivative of this thing, let's just call it omega, because I don't have too many n's going around here. Okay, so if you have any point inside, then you can less than equal to a constant times the norm of f in L2 of omega dA. This is obvious. I mean, you could just use the Cauchy interval formula. But what is true is that if you take, and I used this early on, if you take any point in the Swiss cheese, in the certain domain, and you put in a very tiny circle, then you can just, by continuity, you can control the norm of evaluation here for derivatives or bounded point derivations uniformly on any compact subset, away from the point where you're putting a little circle around. So I'm going to use that because as I go along, I'm going to want to control not only the norm of the bounded point evaluations, but several other things. I want to have to prove a theorem which says that, let's see, maybe I can use this color. If I take any set on what's called the outer boundary of the Swiss cheese, then of positive length, then that should be you determine completely RP. That is, no functions in RP can vanish on the outer boundary on a set of positive linear measure. Now, this is an extension of a theorem of Gonchar. And at the same time, I want to control something in the inside, namely logarithmic capacity. And so what I want to prove, I want to get the following theorem. Okay. There exists a Swiss cheese X such that any set of positive, say this one, lambda 1 for house stuff measure, positive lambda 1 measure determines the functions in R. I'm going to stick with R2 because that's enough in R2x. And moreover, if a function f in R2x vanishes, or f equals 0 on an uncountable set, then and I have in the interior of x, and this implies f equals 0 in R2. Now, at this point, needs to be to be defined. What I mean by the interior. So I'm going to look at the first at the exterior boundary, and then the interior. And so we'll have a Swiss cheese that everything is determined. It will look almost like you're dealing with, let's say, continuous functions on the unit disk, or H1 functions. I mean, in the sense that along the outer boundary, the things are determined by a set of positive length. But interior, you can only have uncountably many zeros, not uncountably many, and no limit points inside, basically. Okay, so now some of these ideas. Well, first of all, maybe somebody can consider this because I don't know the answer. The first one to consider a set like this and prove that some relatively open piece, any open piece, relatively open piece, determines the functions in R of x was Keldysh. I have never been able to find any place where he wrote it. Mergelian mentions the uniqueness problem, but doesn't mention Keldysh. But however, both Sinanyan and Gonchar mentioned Keldish's result. So I've stated that in the paper, and I guessed about 1940 when he seemed to have moved on from complex analysis. All right, now, in order to deal with the boundary, I'm going to need to talk about balayage, or sweeping. And here, I'm going to use an idea of Haben. So namely this, let mu, hold on, I want to let omega be a finitely connected region with rectifiable boundary. So in particular, it's the beginnings of your Swiss cheese, okay? So this will be omega. And this is, I'm using this idea from Haben. And I have the feeling it might can be used for other things. Let mu be a finite, complex measure on omega. Then, and for each Borel set, E in the boundary of omega set is nu of E is going to be the integral over omega z of E d mu z. And that should be AZ. No, hold on. Yeah, no, that's okay. D mu Z, where omega ZE is harmonic measure of E relative to omega and computed at the point Z in omega. So you can think of harmonic measure as also as a function. And then if you do that, this implies then that the integral over E of f d nu is equal to the integral over omega respect to dA integral around E of f d omega. Hold on, let me look at something here. See what I did. Hold on. I'll check one thing. Yep, okay. So I'm integrating this thing. That doesn't look like a. Okay, I'm integrating over omega, but
I'm sorry, but where is the measure mu on the right side?
should be
Mu, where is mu in this equality, right?
I'm taking a measure mu.
Yes, but
omega.
mu presence from the left, but I cannot see mu on the right. Where it is in this formula? I understand. Yes, mu is connected with nu, but where is mu in this formula in the right side? I understand. Yes, I understand you, but you.
Yeah, there's something.
But you have written a formula, and on the right side there isn't mu. I cannot see where mu is in the right side of this equality.
Hold on. I'm taking a function mu is I don't know if you need to put z on there, but I'm integrating mu.
Yes.
harmonic
Yes, I understand. Yes, mu. I understand you. Yes.
Yes.
Yeah,
And this.
but where dA it is it means dA or d mu.
d mu.
d mu. Well, thank you. Thank you.
Yeah, that's what was bothering me.
Thank you.
So you can switch this thing here.
Yes,
all
yes.
right, now-
Thank you. Thank you. Mhm.
All right, so thank you for pointing that out. Now I want to, the reason is I'm going to use dA later for the
Yeah.
sweep.
Mhm.
Yeah,
Yes,
I-
yes,
I
yes.
just-
Well. Thank you. Thank you.
Thank you very much. Okay, now I need to say something about logarithmic capacity. Okay. Now I'm going to write U mu. This is a measure. And this, by definition, is the integral of the log 1 over absolute zeta minus x d mu zeta. Okay, this is the logarithmic potential of a measure mu. And then I'm going to define the Wiener capacity. I don't know whether this is standard or not, but is gamma of E equals the sup over mu of E, such that the sup over Z of u of the logarithmic potential. Oh, yeah. Oh, I keep hitting the wrong one. Okay. The sup of u mu of Z is less or equal to 1, okay? And the logarithmic capacity, that will be CAP capacity of E be defined to be E to the minus gamma of E, okay? And I'm just going to mention two things here because it gets used. But okay, so I'm going to let let an of x naught, standard kind of thing you see in to the z, such that 2 to the minus n plus 1 less than or equal to absolute z minus x naught less than 2 to the minus n. So it's one of these standard annulus. Okay, now there's what I need to know is this thing. Here's a definition. E is thin at x naught if the sum n equals 1 to infinity of n over this thing, E intersect a n x naught is finite. This is the Wiener criterion. Okay. Now, I need to know two things about this function. So lemma. I'll call it 1, but I don't know if I'm, so if I have a collection of sets E, so that the union has finite diameter. So so any collection, finite or infinite. Then and of finite diameter. Let's say in a ball, a diameter less than 1. So put in a ball of radius 1/2, which I can do. Okay. Then, now logarithmic capacity isn't subadditive, but this thing works as follows: 1 over the capacity of the union of the ENs is less than or equal to the sum over n of 1 over gamma of En. En is the En is just E intersect AX naught. I'll need that later. Now here's one that's critical. Lemma. This is due to Denis. If E is thin at a point x naught, then radii issuing from x naught almost all issuing from x naught enter into well, I guess I'll say it the way it was, so I don't have any. Those radii meeting set E. In a set converging of points, converging to x naught meets the unit circle in a set of capacity 0. So what I'm saying is, if you're at a point x naught, then almost all radii move into E for some distance before they hit a complementary thing. So this will be important. Now I want to begin the construction and show where these various things enter. So I'm going to assume that dj rho j, these are disks about zj of rho j, have been determined. Okay. Then the next one, where W. Now rho n is going to always be less than 2 to the minus n to the alpha, or some alpha bigger than 2. Now, this is something that I'm taking this construction beginning with an idea of Gonchar. Now, Gonchar had alpha equal 2. But what I want to show is something a little more. And for that, I think you need bigger. I'm sure you need bigger than 2. And this is for all n equals 1, 2, and so on. Okay. So now what happens at the next stage is the following. So let me put a big picture here. And you're gonna have, I'm gonna have some circles already in. Okay, so now I'm gonna pick a point, ZJ plus one, ZN plus one. That's it, and then I'm gonna look at a square about that thing. Let me see if I can make it so you can see it a little bit better. Okay. So I'm gonna pick a point. This will be Zn plus one. Now this a disk here, this square. So Bn plus one closed square, is going to be a closed square Zn plus one rho n plus one. Okay. And I want this to be contained in omega n, the previous thing. Now the idea is to put what happens next. Now I'm going to put let's see, let me put this here. I'm gonna assume that I always had squares like this. This outside thing is supposed to be rectangular pieces. Okay. So and that will come into play much later. Now suppose I have yeah. Okay, so then I'm going to put in a disk, a very small disk here. Okay, so yeah, so I want to so this new disk here, D n plus one, is going to be equal to a disk of Z n plus one R n plus one, where R n plus one is less than rho n. Okay, so much smaller. Now, the question is, how much smaller do I want to put this? So I'm going to go back here and make a little, so let's En be the union of all closed sets E contained in the boundary of omega n, such that Hausdorff measure 1 is bigger than 1 over n. Okay, and I'm going to set alpha n to be equal to the infimum of the infimum of omega ZE relative to omega n, the harmonic measure, taken over all E in n and all Z in the boundary of Pn plus 1. So, in other words, if I have a set E in the boundary of the omega n, I'm going to move to the next set. I'm going to put in a little square. And then I'm going to, the square I want, because ultimately I want to have this construction be filled out by a Swiss cheese composed of linear pieces. So I can apply the Gonchar-Kalaman theorem later. All right, so but now take the infimum of this thing, and so now here, so here, alpha n is certainly positive. And I've put this now. When I put this disk in with Rn plus 1, what I want is this. I want the harmonic measure of Z on the boundary of Dn plus 1 relative to omega n plus 1 to be less than alpha n over n plus 1 squared. And then ultimately, X is going to be equal to the closure of the unit disk minus the union from J equals 1 to infinity of these new disks that I put in. Okay, now I want to make a computation. What the idea here is that when I put this little disk in, I don't want to disturb the harmonic measure on any of the other previous pieces of the outer boundary. Okay. Now, as I do this, and I'm not going to keep saying it, but I can keep letting n get bigger at each stage of the game, so that I'm getting more and more sets of positive measure. In fact, eventually all of them. All right. So, okay. Now here's what's so here. Then I can get on to something here. So for any Z in omega n minus the Bn plus 1, and any little set E in En. So that means that it's on the outer boundary, but the Hausdorff measure is bigger than or equal to 1 over n. Then you have the following thing. Let me get this in here. I don't think I can make this any sharper, but okay. You have omega Z E relative to omega n plus 1, all right? And that's going to be bigger than or equal to the harmonic I don't know how I managed to do that. This is bigger than or equal to the harmonic measure of Z relative the measure of E computed at Z, but relative to omega n minus the harmonic measure of Z on the boundary of Dn plus 1 relative to omega n plus 1. Okay. That just comes from looking at the maximum principle. Now, this thing is bigger than or equal to 1 minus 1 over n plus 1 squared times the harmonic measure of Z E omega n. And this follows, this part here follows from this, call it star, I guess. It follows from that. So now you can keep going.
Jim, I'm sorry. Could you explain the last inequality?
This one here?
Yes. Why it is so? Yes.
Oh, because of this estimate here on this piece that I'm subtracting. This thing
Okay.
here is this is the inf of here is the inf of
Mhm,
harmonic measure of on omega n, all right? But
mhm.
the 1 plus n squared. So that's where this comes in. This is 1 over n squared minus this thing.
Well, thank you.
Okay, so this is very important. And what happens here is so you keep this up. And I'm gonna try to so what you get is omega z e. And now if you keep doing this, okay, what you get is this is bigger than or equal to the product from k equals n plus 1 to n plus p of 1 minus 1 over k squared omega ze omega n. So in other words, I'm not the harmonic measure relative to these new sets that I'm putting in. The harmonic measure here relative to, I put this little d in, it doesn't disturb harmonic measure on the outer boundary for any set of Hausdorff measure bigger than or equal to 1 over n. Okay. And it keeps going like this. And so let me give you a summary, because this I have to carry on elsewhere. And I realize that this thing is, I find it complicated. I mean, no doubt about it. And so I wish I could make this larger. Why can't I do that? But see if I can. Ah, look at that. Now, took me time to remember. All right, so here's what's going to happen when as you're putting in these disks, these squares. The this thing here, this is valid. This is valid for any fixed n bigger equal 1 and all p bigger equal to 1 whenever E is a sufficient Hausdorff measure. Z is in Gn, which by definition is omega n minus the union from n plus 1 to infinity of B G bar. And then we put G is the union of the GNs. Okay, so what I'm going to have here, I'm back in, well, okay, go back here, right here. I'm putting in, let me make it bigger. I'm putting in these things, and then I'm taking little squares and very tiny, oops, then very tiny disk inside, which will to the next, which is gets you up to the next level. Come on. And when I do that, I don't alter the Hausdorff measure of any of the any sets on the outer boundary. Okay, that's the idea. So and ultimately this set. So let me go back and make a summary, and say just to summary. dk is equal to disk the disk centered at zk, radius rk. The rk is much smaller than the rho k, where rk is less than rho k, and rho k is like 2 to the minus k to the alpha for some alpha bigger than equal to 2. And for any fixed n equal 1 and all p bigger or equal to 1, we have the following thing. The harmonic measure of z and e in omega n plus p, that is, as you move along, is bigger than or equal to 1/2 the harmonic measure of z e omega n. That comes from this thing here, okay? And this is for all e n plus p. So I can as I'm doing this, I can make smaller and smaller disks, and so that I'm looking at sets whose measure is no bigger than 1 over n plus p, that kind of thing. And z in g n plus p, which is omega n plus p minus the union from n plus p to infinity of b j bar. So the thing, I'm going to call this one double star. And the whole point here is that
Jim, I'm sorry. Minus union from n plus 1 or n plus 1 plus p.
N plus p. Sorry. N plus p. Thank you.
Thank you.
So you have, in other words, as I go along, I'm not increasing the harmonic measure at these sets on the outer boundary, and I can control them. Now, this is where I want to get into boundary values, okay? And let me say this is now, in order to get to talk about unique sets on the outer boundary, I have to have something corresponding to boundary values, but there can't be boundary values in the usual way. Okay, so now I'll begin by I'll have just so you can, here's omega n, and I'm going to let nu n be equal to the sweep of area to boundary omega n. Now this is the reason back earlier I got confused and I had an A when I was talking about Haben's thing, because I was thinking of ahead with this one. So here, well, it doesn't work at all. So here nu n of E is equal to the integral over omega n of Z E dA. This is the harmonic measure for omega n relative to and computed at Z. All right. Now let's note here that nu n of E less than or equal to C, where C is independent of omega n and any set E in the boundary of omega n. It's the bounded measure. All right. Now, by construction, this is what we have, that the harmonic measure of Z on the boundary of dn plus 1, comma, omega n plus 1 is less than 1 over n plus 1 squared. Okay? This was a thing I had before, but I'm not worried too much about the Hausdorff measure of the set. Okay. This would follow from what I had before. And this is for all Z in omega n minus Bn plus 1. That's the way this thing was constructed. Now, so by star or double star, either one, what you get now is omega ZE omega n minus omega ZE omega n plus 1. This is going to be less than or equal to harmonic measure of Z on the boundary Bn plus 1 omega n plus 1, which is going to be less than 1 over n plus 1 squared. So that this estimate, I'm just taking that the inequality I had in star and reversing things by taking some things to one side or the other. Okay, so there I have that. Now, and this is for all Z in omega n minus Bn plus 1, and all for all sets E contained in the boundary of Dn. All right, now because since now I had this absolute Bn, that by that I mean the area, that's going to be less than 2 to the minus 2 to the n to the alpha. If you so where alpha is bigger than 2 and all n equals 1, 2. So these sets here, the Bn, the sets that in the complement of the thing I'm constructing, is going to give me the following: that absolute nu n of E minus nu n plus 1 of E is less than or equal to, I got a constant over the integral over x of 1 over 1 n plus n. Yes. Now I've switched. This thing involves integration over omega n plus 1. So you have some. You're omitting one of these. The difference between when you computed nu n and this one is a square, a very small square, or a very small area. So this could be epsilon, but it's so small that I can just integrate over all of x. And so what happens then is this. So this is less than or equal to here. This is less than or equal to C over n plus 1 squared. All right. Now, if you add and subtract intermediate terms and keep going, what you're going to wind up with is absolute nu n of e minus nu n plus p of e. That thing is less than constant times. Now you have this 1 over n plus 1 squared plus 1 over n plus 2 squared plus 1 over n plus b squared. Okay? Or, so this is the tail. This is a tail of a convergent series. So it goes to 0. So therefore, what you can do here is that you have the absolute value of nu n of e minus nu m of e, that thing, is going to be less than epsilon whenever n and m are sufficiently large. Okay, and so therefore nu n for n equals 1, 2, so forth, those measures converge in total variation. And characterized by the fact that nu of e converge relation to a measure nu, and that measure is characterized by the limit as n tends to infinity, nu of e, nu n of e. Okay, so now what I'm going to do is I'm going to describe how we get boundary values, and then probably I'll whisk through the latter part of the thing, because I'll really run out of time. So suppose that function f is in R2 of x, that is the completed thing. And let fk, rational functions, they go fk tends to f, okay, in L2 of x dA. Now, because nu n is the sweep of dA on omega n, okay, to boundary omega n, sweep of the area measure. Then we have here the integral around E of fj minus fk d nu n. All right, and that's going to be equal to the integral over omega n. And now here's that's why there's where the dA comes from, because that was the sweep, the measure was swept, times the integral over E of fj minus fk d omega n. Okay, now I can take absolute values here, all right, and put absolute values inside this one, all right? And I claim that this is always less than or equal to constant C times the norm of Fj minus Fk in L2 of omega n. Okay? And the reason that I have this inequality right here is that if you look at this integration here, integral around E, this thing, integral over E of Fj minus Fk d omega n, that's this is the harmonic extension of this boundary function into the inside, okay? And so what if you were to take and split Fj minus Fk into, so split Fj minus Fk into real and imaginary parts. And then each one of these for this one into positive and negative parts, okay? So if you take the part of the real part here and look at the negative, positive, negative parts, well, the extension, wherever 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 the positive part is situated, but these things are on some smaller set, maybe E. So when you extend it inside, the extension is less than the extension of the actual part that you split off. Okay, so they all and they less than or equal to everywhere inside. And you do this with all those four parts, and since this is true for every Borel set, you can get this inequality here. And then finally, now what happens here is, let's look at the, so as n tends to infinity, you have the integral around E. Oh, let me get rid of this thing. You have the absolute value of the, oh boy, how did I get green ones? Well, okay, we'll leave it. In over E of Fj minus Fk d nu is less than or equal to constant times the norm of Fj minus Fk in L2 of x dA. All right? And this is satisfied for every Borel set E contained in the boundary in the outer boundary. Okay, because I'm using here the fact that Fj minus Fk is bounded from fixed J and K, okay, on E. And this measure converges in total variation. So if I had this, if I've taken the limit, well, here we're here. If I'm taking a limit here, then since this thing converges in total variation to nu, then on any bounded piece, this is no for fixed J and K, doesn't have any poles on the boundary, and so it actually tends, this thing here actually tends to the integral over E of the same thing d nu with it. All right, so now you have this measure nu on the boundary, and then which is satisfied for every Borel set. using the same argument again, you have the integral on the boundary star x of absolute value of fj minus fk d nu is less than, let's say, 4 times the norm of fj minus fk in L2 of x. 4 times, because I'm splitting it, I've split the function here, this thing, into real and imaginary parts, and then each one of those into positive and negative parts, and see how big things can get. And so I get this thing. Okay. And so what happens here is, therefore, fk tends to some boundary function f star in L1 d nu. D nu is a positive measure. And so, and this is the boundary function. All right. And now, I'm going to go quickly on this one. So if you're back here on the, oh my God, how am I going to do this? I can, yeah. Then where's the black one? No, it's not black one, I don't think. Well, I don't know what's going wrong with I can't find my black.
There's another color.
Yeah, well, let's see. What's this one? No, I don't know. So I'll go back to red here. This is crazy. I see. I don't know how I can lose the color, but anyway. What happens is now, so you have this measure here, and this thing d nu is mutually boundedly absolutely continuous with respect to harmonic measure, the way it was pulled out, observing the harmonic measure in all these guys. Okay, so we're on the outer boundary. If let's say you have some portion of the outer boundary, a positive, this is mutually bounded. So if you're vanish on some positive measure, then Jensen's theorem will imply that if f equals 0 on E implies f is equal to 0 in the interior everywhere, because you can apply harmonic measure here relative to this point and take limits, and that's how you get that. Now finally, and this one I'm going to go real fast. I can't believe add a color. Well, that's very strange, but I guess I'm going to have to use the red ones or something, because black has disappeared, which is beyond me. Okay, so now one of the things that you can show here, as you're you have this G, which is the interior, and if you take the bound, take x naught. Oh no, hi, man, this is nuts. Take this one. If you have x naught equals boundary is equal to x minus g. Okay, this thing, and what there is some maybe very small thing around here on the outside, where so this implies that the capacity of x naught is 0. So anything off, outside the interior, but not on the outer boundary, will have capacity 0. That follows from the way we took out the squares. Then, so if you want to get to the inside what you have to show is that here's X and here's Y, that you can get close to this thing here. Okay, what I'd like to get what's happening here? Yeah, okay. So I want to know that I can get join these two things by a line that's like small, so that this the length of this thing it is less than or equal to 1 plus epsilon times the the length of x minus y. Okay. Now inside the interior, I haven't shown though, but you can take derivatives of all functions inside the interior. Arbitrary approach. And so what happens is that if you the way that you get something of arbitrarily small length, almost is that if you're at some point, if you're at some point here. Now remember, almost all lines pass through and only hit finitely many of these squares. Now, since X is in the interior, it's the complement the complement of the interior is thin here, and so since the capacity, well, it means that if you take it small enough, then you can make these little discs that you might meet very small. So you might go like so, okay, and you can control the length. And then what happens is if you integrate along these things, so this is X. So if you integrate, well, if you take, I'm going to finish this. I know I'm leaving a lot out now. But you take f of x minus f of y is equal to the integral of the small thing here, f prime of t dt. Now, look, I said I was going to keep these stages inside a series of Swiss cheeses bounded by polygonal curves, which okay, so, and this thing turns out to be this is the integral. This is what let me write it down, and then I'm going to stop here because it's getting kind of, yeah. So what you can get here, this is equal. So this is equal to this thing, which is equal to f prime of x times x minus y plus the integral over L of epsilon of t dt, where epsilon of t is just equal to f prime of t minus f prime of x, okay? But now, since I'm in the interior, and I've controlled the derivative, all the derivatives, this thing tends to zero uniformly, okay? As y tends to x. And then you can divide through and you get, so finally, and this is it, f of y minus f of x over y minus x minus f prime of x. That thing is less than or equal, maybe I should have had 1 plus epsilon in there, times epsilon of t max, times the max. Which tends to zero uniformly. And so all these derivatives, f prime of x, is called the fine limit as y tends to x of f of y minus f of x over y minus x. That is, you can compute derivatives in any way whatsoever through the interior. Okay, G. Now the final point is that G is the union of all of these Swiss cheeses bounded by polygonal curves. So now let's suppose that a function, let's assume that f equals 0 on an uncountable set inside the interior. Then by the Cantor-Bendixson theorem, you may assume that S is perfect uncountable set, okay? And you may assume also that S is contained in EK because and then now, so you have an uncountable set, all of whose functions are her points with 0 on this set, and so therefore f the n is identically 0 on S. All derivatives are 0 because remember you're inside this interior, and the derivatives can be taken in any direction. So you have this 0, okay? And now this is you're inside the Swiss cheese, okay? So then this thing can be, you can connect to any other point of EK by a polygonal arc on which Gonchar Parlemon satisfied along. And so you would get then that F is identically 0 on each EK, and therefore that's the end. So you cannot vanish on an uncountable set. I'm using the Cantor-Bendixson theorem. I'm going to stop there because I've been going a long time, and I didn't realize, well, I did realize to a certain point that this is a complicated business, but my contribution was to get these boundary values, and then this to prove this part of it here. I gave a new proof of theorem of T.J. Lyons, namely that you can differentiate, that the function is monogenic, if you like, on the E interior. That means that you can compute the derivatives in any way over points in EK. So I'm going to stop sharing, and maybe I am. Yeah, how am I going to do this? I can't, well, stop sharing. Oh yeah, stop share. Okay. Yeah, if I don't know if you have any questions. I know that was kind of pretty fast, but thank you, by the way, for I don't know who it was that when I had that DA in the wrong spot at the beginning, it just that I was thinking ahead, and so where are let me see if I can find any participants. Oh,
Sorry.
lots of people.
Well, thank you very much, Jim. Does anybody have any question?
Yeah.
Other questions or comments, please?
So Nikolai, that's Nikolai Shirokov on the thing.
Yes, I am here. Yes, but well, I understood your lecture well. Thank you.
Well, I have but some of you made some very good comments. And Vasily Vasunin, my guide to the Hermitage is there. And also, what was the one I wanted to say? Well, a number of you I know from long past, but Nikolai, I noticed we have a paper in the same issue of Algebra y Análisis.
Yes, 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 yes. Thank
Well,
you.
if you
Okay.
could send me a copy of your
Mhm.
paper, I will
Mhm.
send you a copy of mine
Well.
Okay.
by email.
So,
Yeah.
are there any questions?
Well, anyway, thank you very much. I mean, if I
Well,
no,
thank you. Thank you very much for coming and for giving this talk. And you are welcome to come again
Well, thank you, but
whenever you want.
well, thank you, but I really enjoyed it, and I'm like a number of people like Baranov and Alexandrov, I guess, and Vasily Vasunin was, and Nikolai Shirokov and yourself go back to the old days, and which I very much enjoyed. And my favorite conference was always the analysis seminar conference you had in late June, and maybe someday it will return.
Okay, so
Yeah.
well,
Anyway.
you are welcome.
Thank you, and thank you for allowing me to talk about this. And
Thank you for your talk.
Well,
Yeah.
glad to
Thank
see
you very
you.
much.
Jim. Good to see you. Yes. Wow.
so I will get off, and you can all go and have some lunch or some dinner, evening. Or to go to bed. It must be late there now.
Okay.
Okay, well, thank you, and thank you. I don't know who, by the way, and I'm not asking, but the referee's report on my paper was very, very good. Whoever did it looked at it very carefully, and I appreciate that. So, okay, so I will leave and with what do I say? Большое спасибо. Я вам очень благодарен.
Большое спасибо вам.
Thank you very much. Thank you
Thank
very
you very much. So we stop right now. Well, the next talk is by myself. It was announced next Monday. And now, Jim, bye-bye. Thank you.
Okay, bye-bye.
Bye bye. Bye bye. Glad to see you. Yes.